Hello everyone, now let's have a look at central limit theorem. The first question to answer is sampling distribution. What is the probability distribution of a statistic? For example, if we take a random sample from the population, x1 to xn, and then we compute the statistics like x bar, sample mean, and s squared, sample variance. The question is, what is the distribution of x bar and what is the distribution of s squared? This is called a sampling distribution. Central limit theorem gives us the distribution of sample mean, which states if x bar is the mean of a random sample of size n taken from a population with mean mu and finite variance sigma squared, then x bar is approximately normally distributed with mean mu and variance sigma squared over n. As we can see, the mean doesn't change, but the variance, because we do the average, so average actually reduces the variance of sample mean. And if we want to do the standardization of x, we use x minus mu divided by sigma. And the standardization of sample mean is x bar minus mu divided by sigma over square root of n. And z is standard normal random variable with mean 0 and standard deviation 1. There are a few notes about central limit theorem. If sample size n is greater than 30, it does not matter what kind of distribution x follows. X could be normal, uniform, binomial, exponential, and Poisson or any other distribution. X bar, the sample mean, is always approximately normally distributed. However, if n is smaller than 30, that means if we have a smaller sample size, the approximation is good only if the population is not too different from the normal distribution. The presumption of normality on the distribution of x bar becomes more accurate as the sample size becomes bigger and bigger. As n increases, the mean of x bar remains mu for any sample size, but the variance x bar getting smaller. Getting smaller means if we increase the n, the variance actually gets smaller. To summarize, central limit theorem tells us for a distribution, random distribution of x, as the sample size increases, gets large enough, then x bar is approximately normally distributed. So the sampling distribution of x bar becomes normally distributed regardless of the shape of the population. So here x is the population. And if we draw sample from x, and then we do the average, the sampling distribution of x bar becomes normal, regardless of the shape of the population. Okay, now let's prove the central limit theorem. So if we have these random variables, and then we calculate the sample mean. So the mean or expectation of x bar, that is expectation of x bar, which equals to expectation of the summation from x1 to xn divided by n. So if we take the expectation sign into the parentheses, we got a 1 over n mu, and we have a total of n mu. So n and n cancel. So we got the expectation of x bar is actually the mu. But the variance of x bar, we know if we take a constant out of the variance sign, we need to have a square term. So this will be 1 over n squared. And then we have Vx1, that is sigma square, and Vx2, sigma square. And then we got a total of n sigma squared. So this n and cancel the 1 of the n. So this will, the variance of x bar becomes sigma over n. So therefore, x bar is approximately normally distributed with mean mu and variance sigma square over n. Let's do an exercise together. An electronics company manufactures resistors with mean mu equals to 100 ohms and standard deviation sigma equals to 10 ohms. If we take 25 resistors, what's the probability that the sample average will be less than 95 ohms? Sample mean is approximately normally distributed with mean mu and sigma square over n. We know the mu is 100, so we put 100 here. And the standard deviation is 10, so 10 squared over 25. So this will become 100 over 25 will become 4. So X bar is approximately normally distributed with mean 100 and the variance 2 squared. So it's about 4. So Z, let's do the standardization. Z equals to X bar minus mu over sigma over square root of n. So this will become X bar minus 100 divided by 10 over square root of 25. So the standardization will become X bar minus 100 divided by 2. So probability X bar less than 95. So if we do the standardization in both sides, so we got a Z on this side, and then 95 minus mu over sigma over square root of n. Let's do the calculation. This will become minus 2.5. So if we check the table, a standard normal table in the back of the book, we will have 0.0062. But the previous example, we have the population is approximately normally distributed. So regardless of the sample size, and we have 25, right? The sample size is less than 30. And the X bar is still normally distributed. But if we have the population, it's not normally distributed. If we roll a fair 6-sided dice 50 times, this will be a uniform distribution because you could get 1 to 6 any numbers. And because it's fair, so there is a probability of 1/6 to get each of the numbers. Now you roll a fair dice 50 times. The sample size is greater than 30. Now the X bar denote the average of rows. What is the probability X bar greater than 3, less than 4? So these samples are approximately uniform distributed between 1 and 6. So X bar is the average 50 times. But we know the expectation of uniform distribution is A plus B, so the lower bound and upper bound, so 1 plus 6 over 2, that's 3.5. And the variance is B minus A plus 1 squared minus 1 over 12, so it's about 2.916. So still we can, for the sample mean, it's approximately normally distributed with mu mean and sigma square over n for the variance. So let's use the expectation for the mean and right here, and the variance replace the sigma square. So what we approximately get is X bar is approximately normally distributed with mean 3.5 and the variance 0.2415 squared. The question is probability X bar greater than 3, less than 4. Then we do the standardization on both sides. Then it will become 3 minus 3.5 divided by 0.2415 on the left side, and then 4 minus 3.5 divided by 0.2415 on the right side. And this will become Z because this is standardization of sample mean. And then after calculation, we got the minus 2.07 and positive 2.07. That means it's in between of the two values. Then we have 1 minus 2 p probability Z less than minus 2.07. This is Z distribution, and the standard normal distribution is symmetric around 0. So if we have minus 2.07 and positive 2.07, we want to get the area in between. Because it's symmetric, this side will equals to this side. So the area in between is actually the area right here twice, right? So this is the area probability Z less than minus 2.07. So if we combine these two areas together and use 1 minus 2p, so the area in the middle is 1 minus 2p Z less than minus 2.07. And then if we check the table, this value is 0.0192. So then we got 0.96. Now let's do an Excel demo for how to get the normal values. critical values. So it will equals to norm dot s dot distribution. Then we have z minus 2.5, and the cumulative is true. So it's a left tail. So it's 0.00621. So this is exactly 0.0062. Let's have a look at 2.07. 2.07. This will equals to norm dot s dot distribution minus 2.07, and then cumulative is true. And this is 0.01926. So this is 0.019226. And as we can see, probability z less than 2.5 is a left tail. Probability z greater than minus 2.5 is right tail. So for standard normal distribution, it's symmetric. These two are the same. So this will be the critical value, and this will be the area. Please note the area is always less than 1. So the area under the curve is 100%. So here is alpha, the probability, but in the x-axis is the critical value. They could be greater than 1. But if the question is asking you for the probability, or the area under the curve is always less than 1. So if you get a value that is greater than 1, that is not right.